Hi, good afternoon, everyone. Thank you for attending our webinar today. We're just going to give it a few more minutes just to allow any last-minute registrants to sign on, and then we'll begin our presentation. All right, let's go ahead and get started. Today we are hosting another one of our thought leader webinars. Today's presentation is going to be on elevation dependent warming and climate risk. Today, hosting this thought leader session, we do have Dr. Elashvili and Dr. Robert Hellstrom. Dr. Elashvili holds a dual professorship at Bridgewater State University in Massachusetts, as well as Ilias State University in the Republic of Georgia. Dr. Elashvili co-leads several international initiatives, most notably the 7C Consortium, which is focused on investigation of the intersections between climate change and human-environment interactions in the Caucasus region. As a professor of geography at Bridgewater State University, Dr. Hellstrom designs and maintains weather sensor networks to monitor climate change, induced warming, and extreme precipitation in regions with complex landscapes. He takes pride in mentoring students through research projects related to meteorology, apologize for that, and climate, with field locations in the northern Andes of Peru, local farms, local K through 12 schools, and the BSU campus.
Thank you for the introduction.
Yep. Just some quick housekeeping notes. This webinar will run for about 30 to 45 minutes. We will save 10 minutes at the end to answer any questions you may have. You can type your questions into the questions section of the control plane. As a reminder, this webinar is being recorded, and a link to this recording will be sent out in a follow-up email. Now, I'd like to turn it over to Dr. Elashvili.
Thank you so much for the introduction and for this opportunity to present some of our work and some of our recent data from some of our recent studies. So I'm going to start from this first slide, and then I'm going to ask Dr. Hellstrom to continue. But this is just about the big picture, right? About the climate change and what we know about it, let's say, during the past 500 million years. Interestingly, this graph, I like this graph because it has actually a different time scale if you pay attention to. So we're talking about the scale of hundreds of million years at the leftmost end of the graph, and which shows the changes in the climate of the order of 50 to 100 million years, and those are big changes. You can see also a zero baseline basically here, which is an average temperature for a second half of the 20th century, basically from 1960 to 1990. So that's our baseline, and you can see that during the past 500 million years, it was actually warmer than, much warmer, even up to 14 degrees compared to that. Then we are moving to another scale. It's basically in the tens of millions of years. You can see it here. By the way, this during this millions of years of history, some 300 million years ago, we had this Permian glaciation, one of the biggest known to the geology. So moving to the more detailed scale, from tens of millions, then to just millions, and then to the hundreds and tens of thousands, you can see that apart from these global changes in the Earth's temperature, we also have this more kind of smaller scale but more frequent changes of the order of tens of thousands of years. And here we are finally at the rightmost end of the S graph with the last glacier minima, and that's our last glaciation period. diurnal glaciation period, and since then temperature is increasing. So basically the last part here, last section here covers past 20,000 years. And as you can see, temperature is increasing, and we have projected values for 2050, and then for the end of this 21st century, showing us that we should expect temperature to be like maybe by 4 degrees, according to one of the scenarios, higher than the average, and then maybe 8 degrees by end of the century. So the question is how that temperature change happens and how that affects the many different aspects of our planet. So I'm going to ask Dr. Hellstrom to continue with the next slide, I believe so.
Thank you, Misha. So there are several factors leading to global warming, as we know, the carbon dioxide and other greenhouse gases that have been introduced by human activity since the Industrial Revolution has had an increase in the greenhouse effect, and that has warmed the planet. But if we focus more on the mountainous areas, in addition to that background warming, there's also an acceleration of warming at high elevations. And there are three major factors that have been studied by other scientists. And one of my objectives is to show that the same thing is happening in the mountainous areas of Peru. So one is the albedo feedback mechanism that many of you may be aware of in the Arctic, where we have Arctic sea ice disappearing slowly. That leads to a darkening of the planet, and that leads to more solar radiation being absorbed, and that leads to more warming. So that's called the albedo feedback. Same thing happens in mountains as these glaciers and ice pack is receding up in elevation. It reduces the albedo or reflectivity of the surface, and so more solar radiation is absorbed and more heat is produced at the surface, and thus that warms the atmosphere above. Another factor is the latent heat of evaporation that occurs. So as temperature increases, more evaporation occurs, and that increases the water vapor content of the atmosphere. So there's that evaporated water eventually makes its way up and cools and condenses. And because we have more water vapor, that there's more condensation, and that releases something called latent heat. So there's an enhancement of water vapor and a decrease in the reflectivity at these high elevations. And I'm going to let Misha take over this next slide.
Thank you. So yeah, as Robert has just mentioned, now we can see that that warming is happening in different ways at different elevations, right? And then there is another question I would like to address here, that is it just getting warmer, or what are the consequences, right, of this warming? And we know that, yeah, the glaciers are melting, we get more water in a liquid form, the sea level is rising, it's simply getting hotter, right? So this warming has a really diverse consequences. So I just want to talk about the extreme, about the how it changes the extremes. First of all, if you look to the extreme temperatures, right, all over the Earth, we can imagine that it has some kind of normal distribution, this famous bell-shaped curve, right? So with the average temperature shifting, increasing, right, the center of this bell curve, as you can see on this graph, moves to the right. It shifts also towards the hotter, let's say, temperature scale, and that way this tiny right edge of that bell, which covers the probability of the extreme temperatures, is getting larger, as you can see, right? So now we have more days with extremely high temperatures. It's not just an average temperature which is increasing, but the number of the days at which we have higher than usual temperatures. And it also has effect on the warming also has effect on the extreme weather events, not just the temperatures. And specifically, we can speak about the precipitation. So what is happening is that with the temperature shift, temperature increase, average temperature increase, we are getting more events with the heavy precipitation than it was previously. So all of this together contributes to the increased risks, let's call it climate risks, and that's expressed in landslides, in heavy storms, in floodings, in fires, right? In droughts. So that's another consequence. That's another outcome of the global warming. So next, I believe Robert will continue with the next slide, please.
Let me get my mouse on here. Here we go. Okay, so location is very important. There are two study sites. Misha is studying the Kazbegi region of the Greater Caucasus at the Georgia and Russian border, about 42, 43 degrees north of the equator. And my area of study, as you can see on the left here, is in Peru, the Cordillera Blanca of northern Peru. That's the northern Andes of Peru. And if we look at this next slide here, you can see that that is south of the equator and in a region called the outer tropics. Whereas Kazbegi is in the mid-latitudes, so it's affected by different type of wind systems. But the commonality between these regions is they both have permanent glaciers. So that the altitudes are a little higher near the equator, but the consequences are very similar, as Misha is going to explain here on the next slide.
Yeah, thank you. So yeah, as you can see, we will be talking a lot about the glaciers, right? So let me give you a brief overview about the glacier melting, glacier ablation in Caucasus region, and this is one of our studies here done by my colleagues. So it shows on the graph you see those bars represent the glacier area decrease rates, annual decrease rates of the glacier area in percentage. And those are calculated for different time periods. So you can see the time periods up here from 1911 to 1960, 1960 to 1986, and 86 to 2000. So basically the 20th century is divided into three parts, and then we have 3 bars for the 21st century. Of course, we have more data, especially the remote sensing data, and that's why we have more detailed information for the 21st century compared to the entire 3 bars just for the entire 20th century, right? So this shows, as I said, the numbers tell us that the percentage of area has decreased by 0.3% during 1911 to 1960, right? So if we want to understand how this process is developing, we may try to make a linear approximation, right? The easiest way. So and that's how it would look like, the best fit, right? You can see it's not really working well. And so probably this process is more complex. So again, looking to these bars, you can see that 3 to the left kind of behave differently from 3 to the right? So if you try to use only 3 bars representing the 20th century, that linear model nicely covers 20th century, but it is totally wrong for the 21st century. Basically, for the 2020, it shows only half of the actual decrease rate, which we observe now. And same if we try to make a linear approximation for the data from the 21st century, it has totally different rate, right? So we can see that something is happening. The process is definitely not linear. And if we also look to the more complex models, and obviously it would be better to try to use here not a linear approximation, but exponential. Okay, let me see. Yeah, that would fit way better to the data, right? First of all. And secondly, what exponential model tells us that there is an acceleration in this process. The process is not developing with a steady rate, but the rate itself is increasing. And that is also obvious from the studies regarding the ice thickness. So the decrease in, again, annual decrease in ice thickness between 2000 and 2010 was 0.5 meter per year in average in the Caucasus. And then from 2010 to 2019, it has increased 1.5 times. It became like 0.75 meters per year. So we can clearly observe that there is a change in the process. It's accelerating, and we have this break line somewhere from the beginning of 21st century. So here is just one nice video showing us one of the glaciers. It's a Chalati Glacier, and on your right side of the screen, you can see the location of that particular glacier on the Caucasus Ridge between Black and Caspian Seas. And the video shows basically last 2 centuries, a little bit more of change in the glacier of its so-called retreat, right? And you can see how dramatic it is from the beginning of 19th century to the 2 days shape the glacier has, and you can see it basically break apart into 3 different glaciers as of now. So, well, what happens when glaciers melt? Going back to that question I've asked previously. So we just played with the numbers about the thickness, about the area, and yeah, we get more water. But what is most important here is that the glaciers and the mountain systems, they represent quite a complex systems, right? And as it was already mentioned by Robert, even the warming is happening at different rates at different elevations, and then the system of the glaciers at the high mountains with the glaciers, right? It includes the glaciers which are hanging on a steep slope, so-called hanging glaciers. It includes extreme precipitation events, as we mentioned. Sometimes you get almost no snow, sometimes you get extreme snowfall. There is a problem with the permafrost, permanently frozen soft soils mixed with the rock and the water, which is melting. And then we have this glacier lakes and glacial rivers coming out of the glacier. So this is a very, you can imagine, this is a very fragile and very sensitive system, very complex system. And it was with the, let's say, with the linear change, even in temperature, the system had enough time to adapt to the changes. And with the acceleration in those changes, system becomes unstable. It cannot reach the same equilibrium level it had previously. And this is when we have high climate risks. And I'm just going to show you in the next few slides what those risks are related to specifically with the glaciers. So I mentioned the melted water, right? That's the something we should be thinking about from the very beginning. So, and I'm not talking right now about water resources, though that's another big question related to that. But speaking of climate risks, what we got with that accelerated melting, we got more water, right? We got more water, which can be trapped by the glacier, by the debris, and formed into the emerging glacier lakes. And this is happening in many different places in our planet, and of course in the Caucasus region. And those lakes are causing glacial lake outburst floods, so-called GLOF events. And I believe something similar is just happening in Alaska. In Alaska, there is a warming issue. Right now, it's an interesting coincidence with our webinar, actually. So, the dams, natural dams created by debris or by ice, of course, they are not stable. Increased amount of the water and the pressure on those dams, and of course, increased temperature itself. At some point causes the outburst, and then we get the flash flood. But it's not just water, unfortunately. It's a water mixed with the debris, with the rock, with the ice, and it finally forms into very catastrophic and severe glacial debris. And I already mentioned the permafrost, and that's another very sensitive feature, which is directly related to the climate change and warming, but especially to the elevation-dependent warming, because as we can see, as Dr. Hellstrom will show us in following slides, at higher temperatures, and it was already mentioned, at higher temperatures, the warming is happening with a higher rate. And the permafrost, as I mentioned, the soft soils mixed with the rock and water being frozen permanently, it is melting now. And the permafrost line, the elevation line above which the permafrost is sustainable, is also moving up, right? And that means we get unfrozen, soft, and loose material on the slopes. It also related to the exposure. Let's say if it's southern slopes, of course, we have a higher risks of the permafrost being melted and frozen, and if it's a northern slopes, it may stay longer, but it is happening. And the permafrost is itself causing the landslides. The landslide may trigger the glacial debris itself, and I will show you the example of that in a following slide. And it also contributes to the forming of that glacier debris, because it provides a soft material which gets mixed with the water and then travels down the valley with a high speed. So as I mentioned, next slide. As I mentioned, this system has lost its equilibrium. It's not. It's and the things which were not happening previously are happening, and it is starting, and that's what we are observing. We're observing, as I said, in other mountainous areas as well. But I'll give you a few examples from the Caucasus again, from our studies, and it's basically from last 21 year. So you can see the Devdoraki glacier event, which happened in 2014, and looking to those pictures. The event originates at 4,500 meters. So the Devdoraki Glacier is one of the glaciers on the Mount Azbegi, and that's our main focus of study. It has several glaciers on different slopes, and Azbegi itself represents a stratovolcano. You can even see from its shape, and technically it's a kind of active volcano because it was active during the past 10,000 years, but let's say for the second half of the Holocene, it is quiet, so hopefully it will stay so. But what happens is that ice fall at 4,500 meters from the hanging glacier attached to the very steep slope there. And that has developed into the glacier debris. You can see from that image, even by the color, you can see that that's a fresh kind of debris which traveled down the valley. And on this photo to the left, the B photo, you see how that debris has covered, dammed basically the ravine, the valley of the river Tergi. It has created that artificial lake, which later on discharged down the valley and caused another flash flood. And you can see on the top part of that picture, you can even see a small part of the road. That's basically the main road, main highway connecting, going from Georgia, from the south of the Caucasus to the Russia, to the northern Caucasus. And that road was dysfunctional for several months. And usually it is blocked with cars and trucks waiting for their turn to cross the border. Fortunately, everything happened during the daytime, so people saw the increasing water level on that coming down from the mountains, so people managed to escape. And but down the valley there is a hydropower plant which was flooded, and there were casualties among the workers on that power plant. So that's just one event from the glacier debris caused by the detachment of the hanging glacier. And this is a nice photo from the helicopter, which shows the area where that actual detachment happened. And you can see, imagine, yeah, you can see how steep is the slope there, right? And clearly the warming has affected and has played an important role in that detachment. So another event here is, you can see a nice photo taken a couple of years ago. I was there in person. It was taken by my colleague in 2023. River, it's a glacial river, Mestia Chala, and that river is feeding from two glaciers, Tsaneri and Chalat. You can see the location of the glaciers on the map. So it looks nice, right, with that nice bridge and very fantastic place. And down there you can see the techniques they are building the hydropower plant. Guess what, right? So now I'm going to show you a glacier mat flow event happening there in 2019, and this is a video, not the best quality, but it can give you a sense of what is happening there, right? So that was clearly connected with the heavy precipitation. Remember the extreme precipitation, extreme events, and we concluded that there was also this glow type of the event from the glacier lake upstream there. And again, the hydropower plant was completely covered by this debris. So the worst, the most dramatic event happened 2 years ago in 2023, and this is the glacier Tbilisi. It's somewhere in the central part, as you can see from the map. And what we get here, again, the icefall and basically a rockfall from this area. I outlined the area for you. This is the area where the rockfall has happened, and that rock has also moved big masses of ice, and finally everything got mixed and melted and finally formed into the debris, heavy debris. So it has started up here somewhere really far away and then traveled down with a high speed down the valley, and you can see what is happening here. This is the place you are seeing in this photo. That's to my taste, that's the best summer resort in Georgia, high mountain resort, Shovi. So you can see the few buildings surviving, but the most of part of the resort was covered, and some people unfortunately didn't manage to escape to the high ground, and we had the casualties of like 40 visitors were killed by this debris. And just a final remark here, speaking of the hazards, you can see the data from our expedition. I'm in the US right now, but these are my colleagues who held the expedition just a month ago, July 2025, because there is another glacial lake formed on another glacier. It's a Tsaneri glacier on the Greater Caucasus. You can get some impression of the lake, right, from this photo, and you can also see the glacier, right, coming down. And this lake was studied in terms of the bathymetry, so we know the actual volume of the lake now, and also the aerial photogrammetry, aerial survey was conducted, and now we have the digital elevation model of the area. And this is what the lake looks like, and its bathymetry at most it's at even more than 20 meters deep at some places, and it's about 1 kilometer long. And total volume of water, we estimated more than 100 million cubic meters, more than 100, half a million, sorry, not 100, more than 500,000 cubic meters, 500,000 tons of water. And this lake, this glacial lake, has a debris dam here. If you look to the photos from 2013, there is nothing yet. There is no lake. If you look to the photo from 2019, let me bring it in here. You can see it's just emerging, right? And now we have this huge lake already formed, which requires monitoring, requires study. So we need more data. So we definitely need more data, and preferably online data, to make informed and timed decisions and to understand this process, right? How it works. So that's one of the reasons why our consortium was formed, 7Seas, and Caucasus Crossroads Core, Climate Change and Culture Connection, uniting universities from United States, from Georgia, obviously, European Union and United Kingdom. A nice photo collage here shows the glacier Gergeti, another glacier on the Mount Hasbegi, how it has changed from 1880 to 2023. I mean, the changes are dramatic here. So what we are doing right now, we're in a process of installing a meteorological, or call it climate monitoring network, and at different elevations. So finally, to come up with the elevation profile of meteorological and climate parameters. But first of all, of course, the temperature. We will be installing a meteorological station at Altihad at 3,000 meters. You see the Altihad here. They are our sponsors and supporters, and the project itself is funded by Mountainous initiative here. There is an operating meteorological station down there in the small town Stefansminda, and we are going to be installing also several temperature and humidity loggers at higher elevations. And this is the equipment we are basically installing right now. The RX3000, this is Hobo meteorological station with temperature, pressure, solar radiation, precipitation, and wind speed direction sensors. We have integrated also analog model, 4-channel analog model here, so that we have future steps would be installing their ultrasonic snow depth sensor. That's our desire, so that way we'll have information about the specific, very precise information about the snow accumulation. And these are the temperature and humidity loggers, which will be also deployed there, and they can function in autonomous on the batteries for a year. So we will be able to collect the data and incorporate everything into the Liquor cloud of database.
All right, thank you.
All right.
So, yeah. So I just want to move along here. That was a great overview of some of the risk and some of the methods. I want to mention a couple things, a few things that we've been doing in Peru since about 2005. I was called down by my colleague Brian Mark to help out with some hydrology in the mountains. And as a meteorologist, my primary role was to set up some weather stations. And but to give you a context, first of all, this is the location in the outer tropics. So we're near the equator, lots of solar radiation during the dry season. And then we have the trade winds, our primary wind system. And as you can see, that's a very low speed easterly flow. There's a distinct wet season that occurs during our northern hemisphere winter, and a dry season during our northern hemisphere summer. And then there's also known altitude dependent warming in the region, has been studied by Ray Bradley and many others. It's a very complex climate. Again, mountainous areas all have complex topography and different aspects and so forth. 2/3 of the water is fed by glaciers during the dry season, and that supports 250,000 people. as far as agriculture, and then also hydropower. The region that I'm studying, the Cordillera Blanca, is the most glaciated tropical region in the world. So the question is, can we monitor this elevation-dependent climate? And one way to do that is to use some weather stations at different elevations. This slide is just showing you a projection of what will likely happen as far as temperature change with altitude. So starting at sea level, you see, again, this is kind of a almost worst case scenario situation, but about 3 degrees at sea level. And then as you go up in elevation in the mountains, up to 4.5 degrees is projected relative to the pre-industrial. So there's also evidence that in the tropical Andes, there's been about a 1/10 of a degree Celsius per decade of warming over the last 50 years by Matthias Wühli, which was published in 2015. Now, since then, what I've been finding is it's actually now accelerating. So I'll show you some slides that demonstrate that. But the important thing is, with respect to glaciers, as the freezing level, the altitude of the freezing line rises, so does the melting of the snout or the terminus of the glaciers. So this local warming that we're observing in these valleys can lead to accelerated glacial loss and also more instability and more risk. So one reason that we see warming in the mountains is called the negative lapse rate feedback system, whereby higher elevations are warming more rapidly than lower elevations, and that leads to a decreasing slope of the temperature, what's called the lapse rate. And so on the left there, this is what is being seen around the world in many mountainous areas. And so my role is to demonstrate that the same thing is happening in the Cordillera Blanca. So one thing I do like to do is introduce ground-based systems to students. And over, again, since 2005, on and off, been taking students down to come with me to learn more about the importance of studying the climate in these remote areas, and then also recognizing the importance of working with students from universities in these areas and learning from each other. On the left here is a hobo unit, which was installed about 2007 or so, and then another one at a higher elevation in the same area installed about 2011. On the right-hand side, Misha mentioned using temperature and humidity loggers, which other scientists have done as well. We have installed what are called LASCAR units, and students have built their own radiation shields for them. And we make the very best attempt to install them in these polylepis trees at about 200-meter intervals of elevation, thereby keeping them shaded, because radiation air is a significant problem in these regions. So as a result of installing these weather stations, I also incorporated the Day Garrison satellite link, which was created by a former onset employee. He now sells these stations for about $1,000, and they integrate with all the onset computer sensors, But the beauty is now I can view the data in real time. And so here's Casa de Agua, which is in the Quilcahuanca Valley, and then up at the upper portion of that valley where we do have a glacial lake that is being fed by the loss of a glacier. But we can take a look at that in real time, and I can make sure everything's working properly and share the data with my colleagues and with my students. And so this makes it very, very, helpful. And again, we can look at the real-time data for the higher elevation site, the one near the glacier with the glacial lake. And all this data can be downloaded through a download data link, as long as you have the link to the data. And so it's been very helpful in my research to have this, to be able to share information, share it with students, and also share it with my colleagues in Peru. In the Yanganuco Valley, now this is a separate valley, I've had a weather station set up since 2005. And as you can see by the arrow, there are two proglacial lakes, and the glaciers are behind me and to the sides. So to the left, not shown in the diagram, but you might be able to see on the map on the right, is Huascaran, the tallest mountain in Peru. And so this is an area of study where people like Lonnie Thompson at Ohio State have studied the ice cores and looked at the past climate. And here we are studying the present climate. We also have a weather station that was an attempt to set up a weather station at a high elevation site just below the glacier. However, because of the location being close in proximity to a roadway where anybody can travel close to it, and also the local people have every right to this valley to graze their cattle. We lost that weather station, most likely due to theft. And then we set it up again in 2011 and lost it again. And the lesson learned is that community outreach and collaboration is key. And that's something we've been working on. So what I'm going to show you in the next slide here are results from the intermediate sensors. And this is kind of just indicating that since 2006, we've collected hourly data at 4 different elevations. And you can see they range from about 3,900 meters up to about 4,600 meters. And these hourly data were compiled and aggregated and checked. And you can see here the monthly averages. And the most important result of this graph is that indeed in the northern Andes of Peru, lower elevations are warming at about 0.1 degrees Celsius per decade, like Matthias Wühli had in his paper, but higher elevations are warming at a rate 5 times that, which is alarming. Now, with this information, we can also explore the lapse rate feedback. And you may recall that first slide I showed with the negative lapse rate feedback. And this graph has a couple things. The dark black, the black solid line, is indicating lapse rate, and that's the slope of the temperature with elevation. And typically, on average, that's about 6.5 degrees per kilometer. But as you can see here in the mountains, where it was measured, again, near the surface, you can see it's quite variable, ranging from 9 all the way down to about 5 degrees Celsius per kilometer. And that depends on a lot of things. It depends on the season, whether it's we're in the dry season or the wet season. But also there's this background influence of the El Nino Southern Oscillation. So we have in the red here, these are El Nino events, and in the blue, these are called La Niñas, where the in La Nina events, the waters off of the Pacific in Peru are unusually cold. During El Ninos, it's unusually warm, and typically we see this response of lapse rate in the mountains. And then the most important indicator here is this trend line you can see going negative, and this decreasing trend line in lapse rate is proof of the negative lapse rate feedback mechanism. And then finally, I have a slide here just to show you another very important variable that we both mentioned, and that's the freezing elevation. Since 2006, you can see the freezing elevation on average, if you look at the dashed line here, was about 49, just under 5,000 meters. And it has since risen to an elevation of above 5,100 meters. So that's almost 150 meters of rise in the last 20 years. Of course, that's quite alarming and should set off some interest in modeling. And in fact, it has. In the past 10 years, many people have been attempting to model the Cordillera Blanca to better understand what will happen to the freezing level and glaciers and precipitation patterns in the future. And the data from onset and from these smaller data loggers has been critical in providing information for those modelers to initiate their regional climate models. So with that, I think Misha and I are open for questions, and happy to have questions, or if Shannon wants to ask some questions, fine.
Yep, as I mentioned, you can type your questions in the question box, and we'll be certainly happy to answer those. We did have one question come up that I wasn't exactly sure how to answer. One of the participants was asking if the slides will be available post-seminar.
Yes.
Okay. As I mentioned, we are recording this, and we will send out a link to this, but any specific requests, feel free to reach out, and we'll make sure that Dr. Hellstrom and Dr. Elashvili get those out to you. Okay. We do got some more rolling in here.
Okay.
Let's see here. So someone did ask, actually, we had a couple questions come up regarding the specific equipment that you use.
Okay. So in Peru, I've been using onset products primarily, and some third-party sensors. But the equipment, we have temperature and humidity, which is for at about 1.5 meters off the ground. We have wind from a Davis instrument, which is combines wind and wind speed and direction. We also measure solar radiation, the global solar radiation incoming. We measure at some sites some soil parameters, temperature and moisture at the Yanganuco site. I do have data for that. And let me see what else. We've experimented with some sensors to look at cloud detection using infrared sensors pointing it upwards. I've also had some students build their own instruments, which we've connected with the U12 loggers, the smaller loggers, looking at wind speed. They built that with a little electric motor and ping pong balls, and for about, I don't know, $5. So it's been interesting exploring different instruments, but
Thank you for sharing that. And I am always amazed by the ingenuity of some of these students where they can get very creative with using data loggers. And if they don't necessarily have a sensor for it, coming up with their own. So kudos to the future generations that are going to be doing these studies. Something else that came up that's a little off topic, but I think it might be good to touch on, because I know when we did our pre-run yesterday, you had discover some best practices for this. Someone wanted to know, what did you do to prevent further theft of the equipment in the Peruvian community?
yes, excellent question. So the best thing is to get involved with the community and get to know, first of all, the faculty at UNISAM, the local university in Huaraz, which is about maybe 50 kilometers away from the mountain, to get those people involved so that they can, we worked with them so that we could keep the loggers in check, so to speak. But preventing theft is all about people. It's not necessarily putting fences around things, which we could have done as well, but it's about community relations. And the lesson we learned is that that's extremely important. The other thing we did was, with the smaller data loggers, we could make them, well, basically hide them. And as you could see, they're kind of camouflaged and they sit in trees. So those have been the most reliable, actually. And so have the larger weather stations, which the larger ones that have survived have been there without any trouble. Again, with a little collaboration with the Hydrologic Institute in Huaraz, and then also with the university.
Great. Thank you so much for sharing that. I think that's very helpful information. Another follow-up question we had is, could you briefly walk us through the process of negative lapse rate feedback?
The process of negative lapse rate feedback. Well, the lapse rate is the temperature profile of the atmosphere, and that is generally on average about 6.5 degrees Celsius for every kilometer rise. The negative lapse rate feedback is associated with the warming of the upper end of the troposphere, and which is where all the weather occurs. And these mountains are all within the troposphere, but the upper elevations of these mountains are seeing more warming because of latent heat release, because of condensation, and other factors like the albedo decrease. They're warming more rapidly than lower elevations, and the reason is they used to be covered by a very light covered substance called ice and snow, and as that disappears and evaporates, it causes more warming at higher elevations, and that pushes that lapse rate at the top forward. So it decreases the slope. I hope that helps.
Perfect. Thank you for that. Another question we had come up regarding sensors is, do you have any issues with snow level sensors and water frozen around those sensors? I can touch base on that first real quick. We do allow you to integrate some snow depth sensors into our RX remote monitoring stations, as long as it outputs an analog output such as a 420 milliamp or DC voltage. And with those, they essentially use a laser beam to track the snow depth. So you just want to make sure it's going to be high enough so it will be above what the maximum snowfall depth is, and it essentially takes a laser measurement to give you that snow level. So you don't have to worry about any water freezing on that or anything. There's no moving parts. But I will let the doctors maybe explain some other snow depth sensors that they have used.
Well, on my end, again, I have studied snow in the past, but in mid-latitude locations in upper Michigan of the United States. And there we used snow depth sensors, which we really didn't have too much trouble with the freezing over and so forth. But in the tropics, in the mountains, I do not work up on the glacier, but of course there are challenges because of the diurnal cycle of temperature. It can go well above the freezing temperature in the day, and at night it drops down to -10, -20 degrees Celsius. And the other thing with snow depth over the glaciers, from what my colleagues are facing, is the fact that the glaciers not stable, and so underneath you can actually change the orientation of your snow depth sensor, and of course that leads to error as well. But in short, I can't really answer that question because I don't have a lot of experience with it.
Yeah,
Thank you
same
for
about
sharing that.
me. We have not yet started those observations on the snow level, so we're going to learn more in coming years. So yeah, I cannot add anything to this.
Perfect. So I guess that's something we'll stay tuned on. Dana Mishu actually had a couple questions that I'm just going to read out real quick. I can try to answer some of it because it's equipment based, but maybe you can fill in some gaps. They wanted to know, are you also interested in analyzing the change signals in rain on snow events? As with warming intensification, a change in precipitation phase is observed. Do you observe such change signals from your observations? That's really where monitoring a few different parameters, from an equipment standpoint, can be beneficial. Obviously, a rain gauge is not going to accurately monitor precipitation if it's frozen. They do make some tipping bucket rain gauges with heaters in them that would melt that snow and give you a more accurate precipitation reading. But for events like that, especially during winter months or colder months, if you did need to monitor snowfall and rainfall, it would be advantageous to have both those types of sensors, and then you can correlate the data to what the temperature is. So if it's below freezing, you can assume that yes, there may be some, snow in the rain bucket, but it's, you're not going to actually get that data till it starts to melt, unless you have a heater in there for you. And then just to follow up with that, doctors, she did inquire about snow drought, and did you observe any increasing frequency?
I'm sorry, snow what?
Snow drought?
Oh, drought. Ah, well, the biggest challenge in the mountains is distinguishing between liquid and solid precipitation. And it would be nice to have a camera set up, for example, so you could see it. But snow drought is something that's definitely going to happen. There's going to be more liquid form. So I suppose that's kind of a snow drought in the mountains, but monitoring that is very important, and it's something that we're going to be working on, and probably working in collaboration with Onset and Lycor.
Excellent. Looking forward to that. Guillermo Sandoval had a quick question. that I will just briefly answer. Are you thinking of any integration using Starlink and Hobo data loggers? Yes, that is something that Hobo data loggers does have on the roadmap. We do plan on integrating satellite technology into our system soon. As I mentioned, it is on the roadmap, but we don't have a set date on that. When we do release something like that, we will make sure that we let all of our customers and clients know. And typically we do send out an email blast, Twitter blast, things like that. So stay tuned for something like that. Hussein Ibrahim actually had a very interesting question that I would like to hear the answer to. And he asks, could the melting of glaciers lead to a change in the pressure applied to the Earth crust, which would lead to earthquakes or volcanoes, and thus we could draw maps of areas exposed to earthquakes and volcanoes I'm just trying to get this to scroll down, due to the change in pressure, or is the change in pressure not strong enough to cause earthquakes?
Well, there is no kind of direct answer to that. There is definitely, there is a change in pressure, right? The question is how fast that change in pressure is happening, right? So again, if the system has a time to respond to that, to adapt to that, that's one thing. Then speaking of earthquakes, if you compare the stress field related to the tectonics in terms of numbers with the stress coming from the glacier pressure, I don't think the glaciers are that significant to that. I mean, to that bigger numbers of the tectonic pressure applied. It definitely it can contribute to some local small earthquakes. Let's call it scientific earthquakes, which could be recorded by the equipment, but even not felt by the people. Interesting question is about the volcanoes. So I mentioned that Razbegi Mount is a stratovolcano, which technically is considered as active because there is an activity there was an activity during the past 10,000 years, right? So that's a difficult question to answer right away. It's my answer would be that it has to be studied, and we need data. It would require some geophysical studies to understand the chamber, location of the chamber, its depth, its size, the temperatures, remaining lava if it is still there, and then of course understand how fast the glaciers are melting, and then yes, exactly how that pressure removal would affect this entire system.
Thank you so much for sharing that. That does bring us just to 3:02 here. I do want to thank both doctors for presenting today, and I certainly appreciate your knowledge and information that you're able to provide for us. I certainly feel like I speak on behalf of all the attendees today, where we certainly learned a lot about the impacts of global warming and human-assisted climate change. So again, can't thank you enough for doing this thought leader webinar with us today. Again, any questions that we didn't get answered, we did copy all the questions and the participants that asked them. We will get those answers for you. And in the meantime, if you have any other questions, feel free to call Hobo Data Loggers directly. And our number is 1-800-564-4377. And again, with that, doctors, I want to thank you very much and hope you enjoy the rest of your day.
Yep.
Thank you so
Likewise.
much.
Thank you.
Bye-bye.